Thanks very much, Marcus and Jay. Hi, everyone. Great to see you all. And thanks for having me. It's my pleasure. So there's been a lot of talk of models recently in the news. My models will be much, less problematic and much more harmless. So my talk is titled On the Logic of Vector Space Models. And the initial motivation for it is a kind of introspective experience that I can't help but have when I hear someone argue. So roughly when someone gives an argument, say I'm in the at a talk that Marcus is giving, and of course Marcus, right, he's giving arguments, not just making claims, right? So what I think I'm self-observing is that he wants to push me into the direction of the conclusion by giving his arguments. Of course, he wants to do that rationally, okay? But I still feel the push in the direction of the conclusion. And then again, when he wants to argue against the conclusion, I can't help but feel that he wants to push me through giving the premises away from the conclusion. And he can do so with different degrees of success and with different force. So it also seems to me his premises, they can give me a push in the one way or the other with a certain kind of strength, okay? So you get the idea. Usually in other areas, when we would hear about something giving a push with a certain direction and strength, then inevitably, formally speaking, we would think of a vector kind of quantitude. And that's the idea. So I wanna think of content in my talk as a vector. In a sense, I wanna, if you like, dress up the theory of vector spaces as a sort of logical theory and see how far we can get with this kind of geometrical metaphor. Okay, that's the idea. Okay, and if the premises, like here A1 to A2 and so on, they manage to push us perfectly in the direction of the conclusion, then I want to think of that as a kind of deductive inference, and obviously that's what we like in logic. But the framework that I want to build will be broader. So I also want to think of premises as giving me a push sort of in the direction of the conclusion, but not perfectly, okay? But something that approximates the conclusion to sufficient extent. And then traditionally, we would like to think of an argument like that as maybe an inductively strong one, okay? Not a deductively valid one, but an inductively strong one. And indeed, it will be part of my little logical framework of today that there will also be an account of inductive reasoning of different sorts of belief revision, learning, and the like, okay? So just as a warm-up, actually, it turns out that in my framework, you can later study different kinds of consequence relations, but let me start with the one that conforms maybe best to this guiding geometrical intuition that I've just given you. So say I want to argue for A, okay, and I'm giving you as a premise A. That looks perfect, right? It's not particularly interesting, but you feel the push of A and it pushes you towards A. That's fine, right? Here's something that is more surprising, okay? So say I'm giving you something, like an A, it pushes you somewhere, and then I give you another premise and it is not A. Okay, then, well, in classical logic, we know what would happen, right? But in this kind of geometrical picture, it seems to me if A and not A are sort of equally strong, then overall, nothing has happened to me. Okay, so I've been pushed by A, and then I've also been pushed by not A, which sort of seems to take me back to where I started from. So the best that I should be able to infer rationally should be the logical verum, okay, so the trivial information. That should be fine, and that's it, right? So you can see the logic that we're going to construct will be quite different from the standard logics that we're used to, okay? Here's, again, something unusual. So I might give you, you know, ultimately a reason for the conclusion, A, say, a premise, and then I give you A again, okay? But don't think of it in a way that you read a science paper and someone says A and then says A again, right? That's on the backdrop of classical logic that would not be very useful to do, okay? But think of it in a way, someone gives you a reason for A, and then maybe an independent reason for A, okay? So then the idea would be, well, I'm pushed towards sort of in the direction of A, but twice as strongly as if I had been pushed if I had only been given A by itself, okay? So one way to record that logically would be to write A and A in the conclusion. And okay, A and A would then also give us a push towards A, but actually it really pushes a bit farther than just the A, okay? So I can always take back, sort of weaken, if you like, right? So I really have two A's, as it were, and then I say, okay, I just want to infer A, that's fine. I could have inferred A and A. I couldn't have inferred A and A and A because that would have thrice the strength of A, okay? So you can see there is a new kind of thing going on that will be important later. And now I've already talked about two A's. Why not write that actually? Okay, so now you can see, oh, okay, Hannes probably in this Corona crisis got a bit weird. Okay, so bear with me, please. Okay, let me use a slightly idiosyncratic notation here. When I want to record that I have twice the A in the premises, let me write in the conclusion 2 times A. That's harmless, right? It's just a syntactic maneuver. Or I can infer from 2AA, that's fine. That's just what we had before, just written up in a kind of unusual way. But once you're there, you might do the following. You might say, maybe in the premises, I could just as well have A, and that's not a typo. You can see my mouse, I hope that's half an A. Okay, well, that's not usually what we do in logic. But now you have A and half an A, and you track that. It pushes you towards 1.5 of the A, okay? Well, half of A, it's not that doesn't look nice. So why don't we write 0.5 of A in the premises, okay? And also here, and here we had A and 0.5 of A, that's 1.5 of A, and now we can infer A, okay? So you can see what I'm doing here is I put scalars in front of formulas, okay? And these scalars are going to allow me to modulate the strength. Sort of, I keep the direction intact, but I make it twice as strong or half as strong or what have you, okay? So that's a bit like we apply scalar multiplication to vectors, okay? And that's what's going to happen here. But here it becomes a sort of syntactic feature. And to some extent, scalar multiplication will become a kind of logical operation that I built into the calculus from the start, okay? So there's more, right? We have A and A in the premises, then that gets sort of annihilated, right? I have the negation, but not the negation of A and B, but B and A. Okay, so this should be fine, right? We should have a law of commutativity. Then maybe I have a C, they cancel each other out, so I'm left with the C, or I could infer half of the C or so, and that's it, right? Or maybe I have 1.7 of A and B, and then, you know, this has strength 1, as it were, so I subtract one of the A and B's, but I'm still left with 0.7 of A and B, and of course the C, which I can join by conjunction, okay? So something like that should be doable. And instead of having 0.7 of A and B, I should presumably, right, be able to distribute these scalars so that I have 0.7 of A and 0.7 of B, okay? So that will be another thing that I'll be able to do. And then if I don't want to exploit the full strength of the conclusion, you know, I can weaken that by 1/2, as it were. And that will amount to weakening each of the conjuncts, presumably, okay? So this is the same conclusion that we just had. It will be a logically valid argument later in this logic of vector space models. Now, here's another thing that I want to be able to do. So here I have 0.35 of A and 0.35 of B. I should be able to write that also as 0.35 of parentheses A and B. And then maybe I have that A and B is equivalent, right, expresses the same content, is analytic to, what have you, to a D, that instead of saying 0.35 of A and B, I should be able to write 0.35 of D, okay? So I will also allow myself to have equivalences between these factual formulas that I've used to, okay? So in some sense, I don't want to just have premises and conclusions that sort of express pushes, okay? But I also want to say the push by A and B, that's the same push as the push by D, and exploit that in my logic, if I like, okay? There should also be logical truths, as it were, right? No premises, but I should have a law of associativity for conjunction, and I can express that by this equivalence symbol, if I like, okay? And then if I have A and A is equivalent to B, I should be able to plug in the B for the A, because they're equivalent, in this factual premise A, which would deliver a B, okay? You could also think of as a kind of modus ponens if this was a conditional in both directions, okay? So all of the things should be possible, and they will be possible later. And then there will be cases where this is not a deductive inference, but maybe an inductive one, right? So you have a premise E, you draw a conclusion B and F. It's not a deductive conclusion, okay, but an inductively strong one. And that will show up by measuring its strength in a certain way. So think for the moment like 1 could be the maximum strength, but this might just be sort of an inductively strong inference with strength 0.707, okay? You won't be able to determine the inductive strength from just the logical form, but there will be more that enters to it, sort of the meaning of E and B and F and whatnot, okay? But that will also be part of my picture. What the E, B, and F are going to stand for, you'll see later, okay? So that will be a concrete example at the end of my talk. So I hope this has given you already a flavor of what's there to be. Might look a bit weird, maybe it is a bit weird, and maybe, you know, this will be the last talk that I give on this topic. So it's one of the first ones anyway. So this is a very new topic that I'm working on. We'll see what comes out of it, okay? So, but your feedback will be especially valuable at this early stage of the project. So here's the plan. I'll first develop what I call the basic system, okay? So that comes with a basic language, a basic logic, a basic semantics, and then for free, we get a basic system of belief revision in these vector space models. That will be the basic system. I'm going to present it to you. You're already prepared of what's going to come. And then I'm going to pause. I'll say that this relates in one way or the other to bits and pieces that you find in the literature. And then I'll beef up the system, okay? And I'll do that by introducing yet another new logical notion that will be similarity. So ultimately, I'll be able to track the similarity of contents, meaning similarity, if you like, okay? And with that more powerful system, we'll be then able, in the object language actually, to define lots of interesting notions that we're interested in anyway, okay? The strength of content, as I said, induction, new types of conditionals, and way more. And then I'll give you 3 little applications. One will be the Linder example from cognitive psychology. Another one will be the Queen example, so that's from computational linguistics. And the third one will be to do with machine learning, okay? And in each case, I want to claim that the system can offer us a kind of logical take on something that we already find in the literature, but that's usually not looked at from the logician's point of view. But of course, we want to take the logician's point of view in this context, okay? And then I'll draw some general conclusions and evaluate a bit what the prospects of the project might be, okay? All right, so I should say, I don't think with my current setting here, I see the chat window, okay? So maybe if you have a clarificatory question, maybe Markus, you can just ask the person to raise the question, or maybe raise the question on their behalf or so, okay?
Okay, will do.
Thanks very much. All right, so here's the basic language of my vector space models, but in a sense, you're already prepared now for that. So I'll have in this first kind of language, in the basic language, 3 kinds of syntactic entities. Terms, formulas, or more precisely, factual formulas, okay? So intuitively, we use them to talk about the world. And then equivalence formulas, okay? Equivalence formulas, in some way, you could think of maybe as occupying a different kind of language level, okay? A sort of kind of meta level, as it were, okay? Now with terms, it's very easy. In this basic language, I'll take any real number, and I have a way of getting a numeral for it, intuitively a name that denotes that real number, and I can use that numeral as a term, okay? So my language will not be countable, okay? And you might think that's odd. In the more refined language that I will present later, I'll repair that. So bear with me, not much hangs on it. It's just for convenience here, okay? Then I have my factual formulas, and here basically the language is like the language of, say classical propositional logic. It's just that, everything will have a slightly different meaning, okay? So in particular, I have conjunction and negation, propositional variables, the logical varium. The only new feature is that I can plug terms, scalar terms, if you like, in front of factual formulas and get formulas again, okay? But you already know that now from my little warm-up examples. And then when I have 2 factual formulas, I can stick an equivalence symbol between them and get an equivalence formula. And that's the only formation rule for equivalence formulas at this point, okay? So you can't take negations or disjunctions of equivalence formulas right now. In the extended language, you'll be able to do that, okay? But here it will be pure equivalences, okay? It's a flat system as far as equivalence formulas are concerned. And then, as usual, we add some metalinguistic abbreviations. So, for example, we might have a material implication symbol for factual formulas, which we define metalinguistically like we would define material implications, say, in classical logic. But again, let me remind you, it won't be classical material implication that we define. It just looks like that. Or we get a logical bottom, a logical falsum, which is defined as the negation of the logical verum, as just as usual. But again, the logical falsum won't be exactly what you think it is at this point. Okay. You get the idea, right? So don't tell anyone, but the idea is I want to dress this up in logical clothes as much as possible at this point, okay? And then only then at the final moment I'll take off the clothes and you'll see how naked I am, okay? But for the time being, I paint this beautiful picture with funny clothes. All right, so that's the language, and then we'll have a derivability relation to logic. Amongst the premises, we will have factual formulas and equivalence formulas. Okay, so that's why I have this twofold creature here, this pair. F, that will be for the factual formulas. But you've already seen it might make a difference whether I have in the premises A once or twice. Okay, so it makes good sense to let F not be a set of factual formulas, but a multiset. Okay, and since I want to have an easy time to sort of determine the overall direction in which the premises are pushing me, let's restrict that F to be a finite multiset. Okay, that will simplify things a lot. As far as the equivalence formulas are concerned, things are just what you thought they would be. It's just a set of equivalence formulas, and there will be no funny business with respect to them. And then as far as conclusions are concerned, again, they can be factual or equivalences. And now, then there will be structural rules, and the structural rules, they will be sensitive on whether I'm interested sort of in doing something with the factual formulas or with the equivalence formulas. Okay, so with respect to equivalence formulas, everything is just as usual. Okay, like kind of Tarskian relationship, if you like. Okay, no funny business. For example, it will be monotonic. Yeah. But with respect to the factual formulas, the structure will be very much restricted. Okay, so basically, I'm going to impose a restricted form of transitivity, and that will be it. Okay, and this restricted form of transitivity will look like this. Say you have these finitely many factual formulas. Okay, and you're able, in the background, you also have some equivalence formulas to infer a factual formula F2. And say you're also able to infer from F2 and further equivalence formulas F3, then you're able to stick the two derivations together, as it were, have just the initial factual formulas, cut out the F2, and end up with a derivation of F3. And of course, you have to sort of take together all the equivalence formulas that have been involved. Okay, that's the form of transitivity that I will have. You could think of stronger forms of transitivity, but I won't impose them. Okay, and again, as you can already see, my logic will be a substructural one, and that's because of the special status of the factual formulas. Yeah. Okay, and then I have some logical eigenaxioms and rules, which I state in the form of equivalences mostly. So, for example, as I already promised, conjunction will be commutative and associative, and I write this up just as equivalences, right? Or say the conjunction of A with the verum, that's A, the conjunction of A and not A, that's the logical bottom, the falsum, okay? Then there is some, interaction with the scalars, pretty much things that you would expect anyway, okay? So 1 times A, for example, that's equivalent to A. That, well, you thought so at this point, I suppose. Then here's the thing that I can distribute scalar multiplication over conjunctions, right? That's already what I promised. That's a special rule. I can aggregate factual formulas by conjunction. Okay, so that's important. I can weaken, as it were, factual formulas. So I have a lambda A here, I have a mu A here, and these are numerals for real numbers, where the real number for this numeral is greater than or equal to the real number that's denoted by this numeral. Okay, so this is this kind of, if I have A, I can derive 1/2 of A. Okay, so that will be allowed. And I have a substitution of equivalence rules. Okay, so if I have phi of A and B is equivalent of A, then I can derive phi where I plug in B, I substitute B for some occurrences of A in phi of A. Okay, in particular, this will give me this kind of inference that I already advertised before. Okay, and then so far, I hope, I mean, other than this slightly weird thing with the scalars, this should look perfectly reasonable, even from a logical point of view. And then there's the only axiom that, you know, might look surprising at first glance, and it's this one. Okay, the logical verum is equivalent to the logical falsum. Okay, so Marcus didn't change his face just looks the same. So, you know, he's fine with that. Okay, I can only see Marcus now, so that's why I check for his reactions. Okay, I see where I'm pushing him, so I even get the thumbs up from him. That's great. Okay, now it depends, right? So, you know, from a very traditional point of view, that might be the point to turn off the Zoom session, right? Logical verum, equivalent logical falsum, that's enough. Okay, I want to do something useful with my time. But take the new perspective. Okay, so I'm giving you the trivial information. That's the logical verum. It doesn't push you anywhere. That should be fine. Okay, and now I'm giving you the logical falsum, right? The bottom. Okay, and you're a rational agent. What's the push that you receive? Okay, none, I want to claim. Okay, there is no push because you're rational. So in some sense, the effects that the two formulas should have on you if you're rational is the same, namely none. And that's what's tracked by this equivalence. Okay, so from this new kind of perspective, actually this equivalence shouldn't be that odd, but should be something that you ought to expect at this point. Okay, but it's really the only point in this basic system where the logic becomes unusual. Okay, other than that, it looks to some extent traditional. All right. Okay, and then you can start derive rules. Okay, you know, not a lot of surprises. Transitivity, say, of equivalences, double negation, transitivity of the material conditional, modus ponens, you know, things like that. Okay, of course they look familiar, but of course they mean something slightly different than in the standard systems that we would be using. Okay, but still, you get a lot of logic out of that already. Now it's a substructural logic. I already prepared you for that. From A, comma A, I can derive A and A, but not from A by itself with these rules. A single A might not be strong enough. That's the idea. And then also other surprising inferences. So say you have not A and B, and now, you know, you might expect the De Morgan law, but there won't be a De Morgan law like this, at least not yet. I mean, I haven't even given you disjunction as yet. Okay. In fact, what you can prove is that negation is really strong. It sort of intuitively negates all the different aspects of a formula, all the different dimensions of a formula. Okay, so the negation of the conjunction is actually the conjunction of the negations of the conjuncts. It really negates everything that you find in there. Okay, so it's clear that this negation symbol won't correspond to each and every occurrence of negation in natural language. Okay, so you need to use the logic if you want to use it to formalize natural language reasoning. You need to use it sensitively. Okay, but you know, for the time being, let's be creative and see what the logic gives us. Okay, and there is again sort of a kind of justification for that law. Say I'm pushing you through A and B, and then I'm giving you the negation thereof. By the initial thought, this should take you back to where you were. Nothing has happened. Okay. Now, but say the other situation is I give you A and B, and then I take back the A and I take back the B sort of separately, okay, but joined by conjunction. Yeah. Then again, I should have taken back, in a sense, what I've given you beforehand. Okay. So the reversal by not A and B and not A and not B should be the same. And this sort of justifies that they should be equivalent in the symbol, in the system. Okay, and that's tracked by this equivalence. Okay, so both reverse the push that's exerted by A and B. That's a kind of justification for the equivalence. Yeah. Okay, and then you continue deriving more unusual stuff. So for example, 0 times A is equivalent to the logical bottom. Okay. Of course, you know, normally you wouldn't want to derive that. You couldn't even express that, but here you can. And once you're sort of in the mindset of the system, that looks plausible. Or you can do the following. So think of your Logic 101 lecture. You introduce negation, okay? And then students raise their arm and they would say, so say I now have minus A. And then you would correct them. You say, you mean not A. Okay, and then they get into the habit. Here, actually, minus A is not A. Okay, and that's the way to express it, and you can actually prove it. Yeah, so the derivation isn't done. So it's a 26 steps derivation, and this might look tedious, but it's not. Basically, it's like you derive something in the first order theory of vector spaces. Okay, it's as bad or as good as that. The reason why, actually there would be a kind of faster derivation would be that we're very much used to calculation with vectors from high school, from your university studies, from applications and so on. So we have sort of internalized lots of shortcuts when we calculate with vectors. And actually, ultimately, you're going to be able to apply all these shortcuts in my system, because ultimately it's just a logically dressed up system of calculating with vectors. Okay, so don't worry about the 26 lines. There's a shorter derivation. You could give it, but you would take your usual shortcuts, and very soon you'll be able to do that. Okay, and then, for example, the material implication if A then B is nothing but B and minus A. Okay, or abbreviating that a little bit, it's B minus A. And now you might remember again your high school analytic geometry, right? What you have two vectors A and B. What's the vector that takes you from A to B? Well, it's B minus A. That's what we learned. Okay, the vector that takes you from A to B, that's the material conditional here. Okay, and indeed it's by B minus A. So as you can see, there is a kind of geometrical interpretation emerging to all of that. Not a big surprise at this point. So that's the push by A, for example. The push by not A, that's just a reversal. The vector in the opposite direction with the same strength. And then the material conditional is B minus A, so that takes you back, right? That's the A reversal, and then you end up here. So it's this vector. But that's the same like this vector, the vector that takes you from A to B, as it were. That's what you learned in your high school math, okay? And that's exactly the vector for the material implication. So for material implication, there's a nice vectorial interpretation, okay? Which I find cute, okay? Here's a slightly more practical application, okay? So here you're giving premises. What's a king? A king is something that's royal and a man, okay? You might think of, these are atomic formulas, king of X, where X is an unknown entity, okay? So X is a king just in case X is royal and X is a man. That's I express by equivalence. And then you get some factual information about some X that you don't know. What you, by premise, now know about this X is that if X is royal, then X is a king. Okay, and that's the material conditional. If X is royal, then it's a king. Okay, so you might think, what kind of property does this X have? Well, presumably it must be a man, right? So if it is royal, then it's a king, so it should be a man. And indeed, in the system, from these two premises, the factual one and the equivalence premise, you can derive that X must be a man. Okay, and again, you run through the conclusion, and at the end you derive man. So that's how this system is going to work. Yeah. The semantics for it is as simple as can be, and at this point should be perfectly natural for you. So a vector space model is really a pair of a vector space and a valuation function. And the valuation function takes syntactic items into items to do with the vector space. In particular, factual formulas are taken by the valuation function to vectors. Okay. Now, when you have a vector space, you also need a field over which the vector space is explained. And I'm going to make my life simple again. I'm going to determine that field to be the field of real numbers. And for almost all practical purposes, that's a good choice anyway. Okay, so that's what I'm going to do. Now, I should tell you more about the valuation function because, as usual, it comes with semantic rules. The valuation function takes my real valued scalars into the corresponding real numbers. No surprise, yeah. It takes factual formulas to vectors such that conjunction is mapped to the addition of vectors, negation is mapped to the minus vector, the logical varium is mapped to the origin, to the zero vector, and so on, right? And then for the equivalence formulas, I give them truth values, either T or F, depending on whether the value that's assigned to the left side is identical to the value that's assigned to the right-hand side, okay? And that's my valuation functions. That's my semantic rules. And then I can define logical consequence. So that's one notion of logical consequence, but a sort of a salient one. That's the one that I started with here. And it goes like this. You have formulas, factual ones, equivalences, and you can draw a conclusion validly, just in case for all vector space models. Yeah. When the equivalence premises are all true, then, and now it depends, if C is an equivalence formula, also the C formula gets assigned a T value. So for equivalence formulas, basically logical consequence is truth preservation, right? In all models, as expected, Tarskian idea. But when C is a factual yeah, Markus, you have a...
Yes, a clarification question
sure.
from David.
Absolutely.
Yeah, so I have a question about
small t.
Mm-hmm.
How does that differ from the verum? Is t a real number?
It doesn't have to be. It's the truth value for true. And metalinguistically, it could be, for example, identified with the real number 1 or so, okay? But it doesn't really matter. Okay, it's just metalinguistically, you are able to denote the true value and the false value. And for the semantics, it's only important that they are two distinct entities. It could be, you know, number 1 and number 0, but other than that, it's not important. Okay,
thank you. Yeah.
Thanks for the question, yeah. So if C is a factual formula, then this is this idea that I started with, right? It's part of the definition that there must be a real number mu, not strictly between 0 and 1, such that if you add up the vectors that are assigned to the factual premises by our evaluation function, and then you multiply that vector with mu, you get the vector that's assigned to the factual conclusion by the evaluation function. Okay? So for example, say you want to derive P, or you want to logically imply, I should say, P from P, then that mu could be 1, for example. Okay? If you want to have that P logically implies 1/2 of P, then the mu should be 1/2 and so on. Okay? So for the factual formulas, you have this other idea. You sort of take together what the premises give you, their overall push, and then the only thing that you can do is you can sort of diminish that kind of push, but you keep the direction intact. Okay? And it needs to be positive so that it won't become a reversal. Okay, so for example, to take the previous example again, you have the equivalences king is equivalent royal and man. You have the material conditional. We derived from that man, but they also logically imply man. Okay, and that the equivalence gives you a certain identity between vectors. Okay, and then that you can use to show that there must be a mu such that mu times the factual premise gives you the vector that's assigned to the factual conclusion. Okay. So for example, P and not P, they won't logically imply Q. So it's a paraconsistent system. And P logically implies P, but P, Q, two premises, they won't logically imply P. Okay, and the idea is that the additional Q might change the direction of the P. Yeah, so that's the reason. Okay, so it's also a non-monotonic consequence relation. Yeah, so many years ago, again, this would be a good stopping point. That's a weird logic, but by now, at least in philosophical logic, we have a sort of liberated understanding of consequence. So that's not yet a stopping point to the project, I hope. Okay, and as it happens, you can prove that this system, the derivability relation that I determined beforehand, is sound and complete with respect to the semantics. And in fact, the proof is very simple. Okay, so there's not much going on the mathematical side here. Okay. Now, final bit to the basic system. Now, this push idea, right? That's been driving the system from the start, and indeed, the push is always there. And you can interpret it differently. I'm going to interpret it now doxastically, and then the push corresponds to a kind of belief revision. Okay, so what I have in the back of my mind here is a kind of AGM, Algeron, Gerdenfors, Makinson conception of belief revision, right? So you remember that theory from the 1980s. You have a belief revision operator, you have a kind of belief set, what you currently believe in, you're given some evidence, now you revise by some ideas, and then you end up with a new belief set, okay? And then you have some rationality postulates on that belief revision operator. And there's something like this that's already built into this minimal system, this basic system, and I want to show you what it looks like if you present it like that. And you can do it in two different ways. So one idea is that the zero vector could be the agent's present doxastic state. Okay, so nothing has pushed sort of the present doxastic state, that's where I am. And now I get new evidence, as it were, okay? The belief revision people would say, or a new premise, that's the B. And then the B pushes me away from my present doxastic state to a new one. And then once I fix a valuation function in my models, the push will be given by the vector that's assigned to the premise or the evidence B that's given to me, okay? So that's my doxastic change vector that's corresponding to the rational change that's effected by receiving the evidence B. So that's one way of interpreting what will be going on. Another is the following one. So maybe I don't want the origin, the zero vector, to track my present doxastic state, but I have a different picture. So go back in time. That's a thought experiment, but that's what people who are Bayesians would like to do of a certain sort. Okay, so say you're objective Bayesian, then they want to say that at the beginning of all doxastic life, okay? I'm at a kind of neutral point. Who knows, that could be in a suitable probability space, the uniform probability measure or something like that. A natural doxastic origin, okay? And then, you know, while receiving one bit of evidence after the other, you know, they would say I'm updating, okay? Here I'm pushed, you know, somewhere. And then I summarize where I am presently. I'm no longer at the beginning of my doxastic life. I summarize where I am presently by a vector, okay? So I already have a vector that's tracking my current doxastic state. My current doxastic state is not a zero vector, but a particular vector, say V of A. So then I use sort of the push that I've been given throughout my life, okay, to track where I am. So it becomes a kind of place vector, if you remember the natural interpretation of vectors. It can track sort of a change, but it can also track the place where you are once you have a natural starting point. And you can use the system also for that purpose. So then my current doxastic state will be a vector. I get new evidence, and then I'm pushed from that vector to another one, okay? Either way, I can use my basic system to give me a kind of system of belief revision in that context, okay? And here is what it looks like. So let's take the second interpretation, just for example. So that's where I am currently. My present state, my present doxastic or epistemic state, that's given by that vector, okay? It could be, you know, 1.5 of P and 0.9 of Q with suitable P's and Q's, okay? And now I get new evidence. That's the B here. That's the new vector, okay? Could be 0.8 of P and 1.2 of Q. And then I use simply conjunction as my belief revision, okay? So here, you know, I would have to be really more precise if I want to do proper HM belief revision. Is this object linguistic or meta-linguistic? I gloss over these details here, okay? But you get the idea. I add B conjunctively to my A, and that's where I am after the belief revision of A by the evidence B, okay? So that's a very natural belief revision operator that's built into the system. But then these HEM people, they're also interested in contraction, taking away information that's already in my belief system, okay? I can do that. Say I want to take out B again. How can I do that? That's the minus, the contraction operation. It's just revision that is conjunction with not B, because I already know that this takes me back to where I was, okay? So I'm here, I contract by B, that is, I add conjunctively not B, and I end up where I was, okay? So there's a contraction operation that's built into it. And then belief revision people would also deal with expansion, okay? So you throw in the evidence and close deductively. There is nothing like a, you know, immediate direct counterpart to it in that system, but there's something a bit like it in the same ballpark. So say you're on Facebook in your own little bubble, in your own little echo chamber, okay? And you say A, and then your friend says, yes, A, and another friend kicks in, yes, yes, really A, and so on, okay? So that you're sort of, you're getting more and more confident in your beliefs, okay? You can track that. It's a sort of a kind of belief expansion, and you simply get that by, you know, conjunction and scalar multiplication, or if you like, just scalar multiplication, okay? You beef up the confidence in your A by just making your belief in A stronger by multiplying with a suitable scalar, okay? So you can see it's a kind of belief revision system that you get for free once you're in that system, yeah? Now, let me pause here for a sec. So what I've just presented you, you know, is a very simple system, you know, soon we'll be able to do way more with it, but already it overlaps with lots of bits and pieces that you find in the literature. Here's what I'm going to do. I'm not going to discuss them, but if you're interested later in about 20 minutes, let's start the Q&A, and then you might return to it. So there's a dynamic component to it, okay? It relates somehow to quantum logic, to arrow logic, to modal logic of space, conceptual spaces, and so on and so forth, okay? So if you're interested, we can talk about it more. But to the best of my knowledge, it's also not precisely identical to any of those things. Okay, now the system so far, that's not yet interesting enough. So let's make it more interesting, okay?
Sorry, Hannes.
Sure.
Apologies for the interruption. Stefan had a clarification question to the 2 slides
back. Perfect
back.
point to have that question now.
Sorry, 2 slides back.
Sure.
Is A equal to K?
Oh, sorry, that's a typo. Yes, that should be A. Okay. Thanks very much indeed. Okay, thank you. Please. Great, thanks very much. Next time I'll have better slides. Great, thanks a lot. That's exactly right. Okay, fine so far? Great, then let's beef up the system a little bit, okay? So what would you do next on the vector space side, okay? Well, usually we don't just have vector spaces, we like to have inner products, on vector spaces for various kinds of reasons, right? From inner products, for example, we can define in a neat way norms, lengths of vectors, and we want to go there, right? We want to have strengths of contents, right? That was one of the driving ideas. So I'm going to introduce now an inner product, and it's all over the real numbers. You know, why not have the standard inner product? Okay, the Euclidean one, as it were. Okay, the dot product, as some people would say. Okay, so that's defined in the usual way. And the definition, you also have these lengths here. Let's ignore them, right? Say it's all normalized, they all have the same length. Then really what you track when you take the inner product of the vector that's assigned to A and the vector that's assigned to B is the cosine of the angle between them, okay? So, you know, if the angle is 0, so it's the inner product of, as it were, A with A, okay? Well, the vector assigned to A with the vector assigned to A. Then the angle will be 0 and the cosine of 0 is 1, okay? So, you know, in some sense, this is going to track that A is perfectly similar to A, okay? So here's the idea. I use the inner product to measure the similarity of contents that's been assigned to formulas like A and B, okay? And of course, the content of A is identical to the content of A, and that's what's tracked with a similarity of 1, okay? Now, if you took the similarity of B with not B, for example, what you would find is that the cosine is -1, okay? So that's maximum dissimilarity, as it were, okay? And then you could say, if there's a situation like this here, B and C, okay, they're orthogonal to each other, okay? So their inner product gives a 0, 90 degrees, okay? Of cosine of 90 degrees, then this sort of tracks that B and C, well, they are neutral to each other. Or, as we are often saying even in natural language, you know, again, Marcus gives his talk, I raise my arm in the Q&A, I say something, and then Marcus just dismisses what I'm saying and says, Hannes, but that's orthogonal to what I wanted to argue for, okay? So, of course, that's just a silly metaphor, but in this system now, this will not be a silly metaphor. That will be precisely it, okay? So now contents B and C, they can be literally neutral to each other or orthogonal to each other, okay? Neither particularly similar nor particularly dissimilar, okay? Similarity is 0. So that's this new notion of similarity that I'm going to use. And similarity, defined like that, in the system will be a kind of new logical term, okay? Now, if you also want to take care of the lengths, you know, there's different ways of dealing with them. You could divide by the product of lengths and so on. Let's just gloss over that for the time being, okay? But that's the idea. So what I want to do now is I want to revise and extend the system by introducing similarity of content as a new quantitative logical term. There's also other bits and pieces that I want to change. So, you know, we're dealing with an uncountable language, while as logicians, we want to have a countable language maybe. So why not construct the scalar terms like we construct terms in the first order language of real closed fields? Okay, then we get a countable language. That's nice. And then why not be more liberal with respect to equivalence formulas? Say we can apply logical connectives to them. And finally, why not also have quantifiers, okay, that we can stick in front of equivalence formulas and get equivalence formulas again, so that we can quantify over scalars and vectorial contents, okay? So from a traditional point of view, I'll now have, as we would normally want to say, propositional quantifiers in my system. It's just that these propositional quantifiers are really now quantifiers over contents that have vectorial structure, rather than being, you know, sets of possible worlds or something like that. So we have a way richer object language, and we have to adapt the logic and the semantics accordingly. I won't deal a lot with the semantics. You guess how this is going to work, but you know, the similarity function symbol, that will be interpreted as the standard inner product, as advertised on the previous slide. And then I'll be able to define logical consequence just for equivalence formulas, and all the other logical consequence relations for factual formulas. Let me just finish the thought, and then there might be a point, yeah? So I'll be able to define logical consequence just for equivalence formulas. And then if you're interested in having our good old logical consequence relation that's also applicable to factual formulas, I'll be able to define that on the basis just of logical consequence for equivalence formulas and the greater expressiveness of my object language, okay? And then if you want to have an alternative logical consequence relation, again, my guess is you'll be able to define it in terms of my official logical consequence relation and the richer object language that I'm now going to have, okay? Is there any clarificatory question at this point that you want to add? Yes.
Stefan Kaufmann wanted to ask
Hi,
something
Stefan.
about the
Good
previous
seeing
slide. I think your microphone is off, Stefan.
Do you hear me?
Now.
Yes. Hi, Stefan. Hello.
Yes, hi. I actually have a question about the last slide, not this one, but the one before with the little on it, just to make sure I understand this correctly. So you labeled the axes with P and Q.
Yes.
And you have these ABC, so they're all formulas, right? So P and Q are atomic formulas, and
that's
ABC
right. But I should say, that's not what the picture necessarily looks like. This is just to give a vivid picture of what the situation might look like.
Yeah.
So for example, I'm always make it look like in my diagrams as if P would have to be something like a unit vector for one of these dimensions or so. But that's not necessarily the case. Okay.
So it's just an atomic whatever variable.
It's just an atomic formula, and I have a valuation map that for the sake of the example actually assigns to this P, say the unit vector 0, 1. And to Q, the unit vector as 1, 0, and to Q.
Right.
But that's just for the sake of the example, okay?
So I was wondering because so if these are the atomic formulas, so you're sort of assuming that they are independent.
Not necessarily, just in this.
Not just logically, but even. Sorry.
Not generally, Stefan. Just in this example, in this picture.
But if you do this vector calculation, then they are not the dimension labels of your vector space?
No, not necessarily. That's what I mean, right? So if I go back to the semantics, just a sec here, the value of a propositional letter is just any old vector in the vector space.
So it's just, the picture is just a little bit too let's say, I don't know, misleading. I don't want to say misleading, but okay.
Yes, as they are. No, I agree. So, so maybe what I can learn is I thought it would help to have these labels to make the picture more vivid, but I could see that this was misleading in this present case. It's not necessarily like that, okay? It's just that, for example, I used it here. So I wanted to have an A, and I wanted to give you the feel that this is already something, maybe it's of the form 1.5 of P and 0.9 of Q. And in order you sort of visualize that, it's useful to have P here and Q here, because then it's very easy to compute what that vector looks like. That was all. Okay?
I see. Okay.
Good question.
Just assuming, thank you.
My pleasure. Marcus, so I'm going a bit beyond 5 p.m. with my talk because there are already quite a lot of questions. I hope that's fine. So I'm eating a little bit into my Q&A time here. Okay?
No problem
if that's okay. But it's perfect to have this, to have it in that way. So let's be super flexible here. Okay. So that's the extended language, okay? And again, don't tell anyone, but it's the dressed up language of real closed fields, okay? So if you're into model theory, yay, okay? If you're not into model theory, you might still say yay, okay? Anyway, terms are in the first order theory of real closed fields. Factual formulas are what you assumed, okay? Not much funny business going on. I now have new constants here which I call logical units, and they are going to track vectors in an orthonormal basis if you look at the semantics, so sort of unit vectors, okay? But they are not identical with the propositional letters. So I have special logical symbols in there over and above the logical verum, okay? But that's not so important. I could even do without if I wanted to. The only thing that's important on this slide is I have this new function symbol sim. If I apply it to factual formulas, I get a term, and again, it measures the similarity of A and B. That was what I already explained here, okay? And then, as I say, I'm more liberal on the side of equivalence formulas, so I can negate them, and I can stick quantifiers in front of them, scalar quantification, and as it were, vectorial quantification, okay? So I get a full first order language if I just look at the equivalence formulas, yeah? And then I have my metalinguistic abbreviations again, like previous ones, but also new ones. So I have material implication for equivalence formulas. They look calligraphic here. Now this thing doesn't just look like material implication, it is literally material implication, as you're going to see in a sec, okay? Whereas this thing, it looks like material implication, but it's not. It's this kind of vector operation that I had before, because this is for factual formulas, while this is for equivalence formulas, yeah? And then I have the logic again. It's an extension of the previous system, so you still find the basic system. Say, conjunction, that's for factual formulas, is still associative and so on. Yeah, the distributivity laws that we had before, everything that you already know. But then I have new logical laws for similarity. So for example, the similarity of A with respect to B and C is the sum of the similarities of A to the single conjuncts. Okay, so in this way, similarity, the new logical symbol, interacts with conjunction, the old logical symbol. Okay, and we can write it up in terms of such equivalences. Okay, and then there are further axioms. And for the scalar multiplication, you know, I have something that really looks more mathematical. Okay, and I'm not trying to hide that because it's for the scalars, and I'm happy for them to be, you know, sort of real valued, as it were. So basically, what I have here is enough to prove for every function that I can express in the system the intermediate value theorem. Okay, as if you're into, you know, real closed fields, that's what you want here. Okay, and again, we have our old bottom is falsum. Okay, verum is falsum. And that's my deductive system. And then I have two final axioms, and they are interaction axioms for scalars and vectorial contents. Basically, in vectorial terms, they say that there is a unique representation of vectors in terms of these logical units, and that means every vector has a uniquely determined sequence of corresponding coordinates with respect to this orthonormal basis that I'm presupposing here. Okay, so there's a nice way of writing vectors through coordinates. That's what I'm postulating here. Okay, and that's my system now, and I have first order logic. I just have first order logic now. Okay, for the equivalence formulas. And then I adapt my semantics accordingly. Sim now corresponds to the inner product as advertised, and you know, the usual thing. And then, as I said, I only define logical consequence now for equivalence formulas. Okay, so it's truth preservation, Tarskian consequence relation as usual. Okay, and now you want to say, but hey, I want to have consequence again also for factual formulas like we had it initially, and I can do that. Once I have my official logical consequence relation, I can define the previous one, as it were, right, for factual formulas. By doing it like this, I say factual A1 to AM plus equivalence formulas. They logically apply the factual formula C, just in case. Take the equivalence formulas, use them as the premise set, and say that they logically apply in the defined Tarskian sense a formula that I get from the factual premises and the factual conclusion by putting them together in this way. And look what the object language formula now says. It says there is a real number, as it were. Actually, that's a typo. There should be a mu here. Sorry, I apologize. There is a mu between 0 and 1 such that mu times conjunction of the factual premises, that yields the C again. So instead of having this kind of weird new logical consequence relation, I can define the weird one in terms of the traditional one for the equivalence formulas and using the more expressive resources of my object language. Okay, and then if you come around with this new cool, you know, even more fancy consequence relation for factual formulas, my guess is I'll be able to define it with my resources in a similar way. And the nice thing is now the official consequence relation is as standard as can be, monotonic, transitive, not paraconsistent, not substructural. Okay, but if you want to tap into this sort of weirder areas, forgive me, okay, if you're into paraconsistent logic and so on, right? Then you can do that, and here's the method by which you can do it. Okay, so this is my way of bringing together very traditionally minded logicians and the cooler ones. Okay, I can do that. And then my deductive system turns out again to be sound and complete with respect to my logical consequence relations. Okay, and as it happens, this extended logic of vector space models is decidable. Big surprise. Why is that? Because the first order theory of real closed fields is decidable. So what's behind this, this theorem here is really Tarski's result from back then. Okay, quantifier elimination, as it were. Okay, so you get a nice logical system. It's as decidable as, say, classical propositional logic, if you like. Okay, well, not with the same complexity, but it's decidable. Okay, so again, I want to say a nice logical system. All right, so using that system, there is now a whole lot of things that you can do and things that we want to do, philosophically speaking, okay? So I'll just hint at them here. I won't give you the theories, I'll just hint at them. So obviously, we now have strength of contents, right? Because we can define the norm through the inner product, and you can express all of that now through sim in the object language, okay? Sometimes we might not be interested in strength, but just sort of pure content, okay? Or pure subject matter, as it were. You can define that. The pure content will be sort of this half line where you don't care about the length, okay? And if you're interested in subject matter, you might add the other half, okay? And then you get just sort of this direction. So the pure direction, that's subject matter, okay? But in other cases, you are interested in the strength of a premise that's given to you, or the conclusion that you want to infer, and then you use sim to determine sort of the length, okay? So for example, the length of not A is the length of A in this system. Well, they have the same push. That was the idea, okay? Now, for other purposes, we might want to have inductive inferences, okay? So say we have factual premises, okay? Previously, we deductively inferred a conclusion, but now we want to say, well, they don't give you the conclusion exactly, but approximately. It's an inductive inference, okay? One way of defining that is the following. You take the premises, the factual premises, you take them together, as it were. You fix their meaning, so you have a valuation function in the background here, okay? So inductive logic is not as structural as deductive logic is, okay? So there's something material to it here. You have a valuation function in the background. That's why I have a little v here for valuation, okay? And now what you do is you determine the vector that belongs to their conjunction, the conjunction of the premises, okay? And this might be this vector here. And now it doesn't push you exactly in the direction of B, but something that's close enough to B, to the vector that's assigned to B by the valuation function. And you measure that similarity again, as I did before, in the object language by the sim symbol, in the meta language by the inner product, okay? And you measure that similarity by a real number, and then you can say, maybe, you know, the inference here from A to B is not perfect, but it's 0.905, okay? And this tracks the similarity, okay? If you forget about lengths again, their angle, okay? And then you get for free, for example, if you can deductively infer from A1 to AMB, then you'll get always an inductive inference with sort of, if you forget about lengths, the perfect strength of 1. But in other cases, it's a merely inductively strong inference. Then it's 0.905. It's not deductively valid, but it's inductively strong, okay? So inductive inference, in one way or the other, will be done by using the similarity between vectors here, okay? That's the idea. And then you can look at conditionals. So far we had the material conditional, okay? But we, you know, as in classical logic, that's not good enough. We want to have other conditionals. So say you like the Ernest Adams story of conditionals, right? A kind of Ramsey type of story of conditionals. Then usually you would now involve probability measures, and you would say, what's the rational degree of acceptability that you give to an indicative conditional if A then B? Well, that's the corresponding conditional probability of the proposition expressed by B given the proposition expressed by A relative to your current subjective probability measure, something like that, okay? There is a geometric interpretation to conditionalization, to probability measures, where conditionalization corresponds to something like you project the consequent onto the antecedent, okay? So I don't go into the details now, but there is a kind of geometric counterpart to conditionalization, it's projection. And the same idea, you know, you can apply here. You have a vector that's the antecedent A, that's what's expressed by it, right? Then you have a vector that's expressed by the consequent B, and now you project the B vector on the A vector, okay? And you measure its length, so this is this length here, and then you use that length, and you can determine it by the inner product in the object language by sim, okay, to measure, as it were, the extent to which a change, the push by A, conforms to the push that's expressed by the consequent. And you can use that length to track sort of your degree of acceptability of B given A, as it were, of the indicative conditional if A then B. So it's the same Adams kind of style idea, the Ramsey test style, okay? Hypothetically, let's take the push of A and then let's see how much this conforms to the push by B, okay? But it's not expressed in probabilistic terms, but in vector terms. Yeah, and then you might say, but hey, for a subjective probabilistic story, it's always relative to a probability measure. Where does it show up? Well, you could also do that relativized to your current doxastic state. It's just that's not a probability measure, but that would be a vector itself. Okay, and then you would look at the push that's your current vector, their current doxastic state. You add to it the revision that's given by the antecedent, that's A, then you're at this vector, and then you project sort of the consequent vector on that vector, and you use the length of that vector to determine your degrees of acceptability. But you see, a very similar kind of Adams style idea of how to get Ramsey test conditionals into the system. And the neat thing is you can express all that in the object language, okay, and study then the logic of indicative conditionals in this way, okay? So if you do it in the right way, I'm not giving you the details now. For example, you will have the proof of a kind of agglomeration law in the consequent, as we want to have, you know, and so on and so forth. You get the idea, okay? Say you want to have modalities. Why not? Okay, again, for vector spaces, what's the next thing that you want to do? you want to have linear transformations, right? Squeezing vectors or rotating them and so on. And think of all the useful applications that these linear transformations have, okay? If you want to have them here, one way of doing that would be introduce a sentence operator and interpret that box operator by applying a linear transformation. That's effectively a matrix that you multiply with the vector that's expressed by the A, okay? With this little matrix, you would have the A here, and that once you apply that matrix, that linear transformation, you get box A, and you can see what happens here. If A was here, box A is here. So the box operator sort of expresses that you get more confident in this P dimension, but it shrinks that dimension. So you get less confident in the Q dimension. And this could be a useful new belief revision operator for some purposes, right? And then you look at the corresponding logical properties in the object language and you find out, look, this box operator looks like a normal operator in the sense of modal logic, okay? Commutes with conjunction and so on. And indeed, normality for these normal operators, for these modal operators corresponds semantically speaking to these operators expressing linear transformations, okay? So there's a cute correspondence between normality for the modal operator and linearity of the corresponding maps. And again, you know, if you write it up in a proper way, you can write down matrix multiplication in the system. It's already prepared for that, okay? So there's a lot that you can do. That's what I wanted to advertise here. So let me finish my talk with 3 little toy examples, okay? So you can see that at work, and then I'm done. So the one is the famous Linda example, okay? So that's Tversky-Kahneman. I'm sure many of you have heard that at some point, right? So people are given a story in an experiment, right? So it's a story about Linda. She's 31 years old, single, outspoken, very bright, majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations, okay? So you get the picture of Linda, you visualize that, sort of, okay, that's what Linda is like. And then people ask the question, what's more probable, given that information about Linda? That she's a bank teller, that's the B here, or that she's a bank teller and a feminist? Feminist is here. Okay, so let's assume bank teller and feminist, that's sort of neutral to each other, at least approximately, okay? And people were given an answer and they were saying, well, it's more probable that she is a bank teller and a feminist than that she is a bank teller, given the evidence, okay? And then people started complaining, wow, people are so irrational. By the laws of probability, the probability of the conjunction, you know, if anything, right, should be less than equal, presumably less than the probability of B here. So there's something weird, and then other people came along, no, they understand the question differently. You know, the usual debate starts. Here is my vectorial take on what's happening here, okay? So the story that people are given is, if you think about it, a long conjunction. And with the right valuation map, you could break it up into the conjuncts, give vectors to the conjuncts, and then determine the overall effect that the story has on you, okay? It pushes you somewhere. Let's sum up, that's the idea, this push by E here. I don't break it up into conjuncts. And I hope you agree that sort of this pushes you towards the feminist direction. That's what the story does, right? There's nothing about the bank teller thing here. Okay, it's orthogonal to that, approximately. So the push should be somewhere here, close to the feminist axis, but you know, not to the bank teller axis. And then people are asking, what's more probable? B, that's the B vector here, or B and F, right? So that's B and F, right? So that's conjunction or addition here, so that's here. And then my idea is, induction is similarity. What they are understanding is really the following thing, okay? They're not thinking in strictly probabilistic terms. What they do is, they think that, which is more probable given E, that means to them, what is more similar to the evidence that's given to me? Think of inductive inference. What's more similar? What's more similar to E? Is it the B or is it B and F? And they rightly say it's B and F, okay? Because look, that's the B and F vector, okay? That's more similar to E, smaller angle, than the B vector is, okay? And that can be tracked even in quantitative terms, again, in a product, you know. So that's what they're doing. That's my suggestion, okay? And I think that's a neat reconstruction of what's going on in the experiment, okay? And in fact, what one can do, I won't give you the details now. If you're interested, ask me in a couple of minutes. There's actually a nice probabilistic justification of my vectorial system too, okay? Which sort of justifies why negation is mapped to the minus vector and why conjunction is mapped to addition and why the varium is mapped to the zero vector, okay? And why, you know, similarity is what it is, okay? There's a probabilistic justification to the system. Basically, what you can do is you can interpret my system in the way that the pushes are so-called log odds changes, okay? So odds, that's a probability over the 1 minus the probability, okay? You can change these odds multiplicatively, okay? That's what's happening even in conditionalization. And then you can take the logarithms thereof, okay? If you're a Bayesian, you like these kinds of operations. And they show that my vector operations correspond in the intended sense to the logical operations, but with a probabilistic interpretation, okay? And if you have this probabilistic interpretation in mind, then actually my little reconstruction here is not far away from an existing neat probabilistic story, but not a standard probabilistic story. So there is a nice paper by Vincenzo Cruppi, Brandon Feitelson, and Katja Tentori. Vincenzo is a former colleague of mine in Munich from the MCMP. And what they suggested is what people are doing is they don't compute absolute probabilities or even conditional probabilities, but they look which information is incrementally confirmed by E, by the evidence more. Is it the B or is it the B and F? And as it turns out, right, with the right probabilistic confirmation measures, which are not probabilities, yeah, but defined in terms of probabilities, you get more probabilistic push for B and F than for B. And that's their reconstruction of what's going on in the Linder case, okay? But the funny thing is, these probabilistic measures of confirmation, of incremental confirmation and support, right, very often they are defined in terms of log odds changes. And if so, then, you know, if you look at my system with these probabilistic glasses on, that's pretty much my interpretation, because then the log odds changes that you get from evidence, if you want to track the effect that they have by, you know, conditional probabilities and so on, what you get is basically you're measuring correlation. In the geometric interpretation, this correlation corresponds to inner products, okay? So in a sense, what I'm doing when I determine similarities, I'm measuring correlations between changes, okay? And probabilistically, that's what they are doing, but they are not thinking of them as vectors, but sort of in probabilistic terms, okay? So my vector story is even sort of close to probabilistic stories that you find in the literatures, but it's not absolute or conditional probabilities, but confirmation. And again, that's a kind of push, right? It's a kind of support, okay? And what, for example, Katja Tentori and Vincenzo Cruppi in independent work then have argued is that people have a much easier time of judging impact of evidence than determining absolute probabilities of evidence or conditional probabilities of evidence, okay? In some sense, cognitively, impact, support, incremental confirmation might be prior to absolute probability, okay? And they flesh out this idea in probabilistic terms, but maybe another way of fleshing out their ideas might be to use the logic of vector space models, okay? As a new kind of normative yardstick that you can interpret probabilistically, but you need not, okay? Second thought, that was Linda, right? Second thought, the Queen example. So these days, linguists use vectors a lot. Well, linguists of a certain sort, computational linguists, okay? That's a field that's also called natural language processing or distributional semantics. That's what you do if you have a query in Google, right? You write up something. What the software does is they determine from what you write there, from your text, a vector. And then they give you answers by determining similarities between vectors, and guess what? They use the inner product, okay? Or something that's defined in terms of it. And linguists also use that. So these days, very often, they would represent words or sentences or whole texts as vectors. And they would determine these vectors by certain algorithms, for example, by neural network models, okay? So there's a lot of literature that in spirit, actually more than in spirit, is close to what I'm doing here already. And famously, that made the news back then, a couple of years ago, there is this software word2vec, transforming a word to a vector, where the following was observed, right? You take the vector for king, you subtract the vector of man. So you take manhood out of kinghood, okay? And then you add womanhood, you add the vector for woman. And surprise, you end up with a vector that's identical or strictly very close to the vector for queen, okay? And intuitively, if you take man out of king, what are you left with? Well, being royal. And then you add the information that it's woman, so a royal woman, so this is a queen, right? So it makes sense. So vector operations seem to all of a sudden to make sense. So maybe there's a lot that you can do with these vector operations that also make sense from the more semantic point of view. Okay. Now, actually, you would expect just that with my system. And in fact, it's very easy to give sort of a reconstruction of this queen example in the language that I was presenting. Okay. So the only thing that you need to do, you need two premises. A king is a royal man and a queen is a royal woman. Okay. And then you crunch the machinery. Even the minimal system, the basic system that I had would suffice. You don't even need to use the extended system. And then you can show that king minus man plus woman is queen, or in my terminology, if man then king, so must be someone who's royal, and woman, this is equivalent to queen. Okay. And you can derive that just by the laws of the system. Okay, so actually there's a linguistics literature out there, and ultimately coming now from the logical point of view, we might build a bridge to some of these results as well. And then final idea for today, there's also something like a logical reconstruction of machine learning in the offing that in the future may be quite interesting. At least that's what I hope. Okay, so here's a super simple example for that. Take the simplest neural network that you can think of that's able to learn. What is that? Well, it's perceptrons. Okay, so now we are back in the 1950s. Okay, Rosenblatt. Okay, so what did he do? He had a very simple neural network, basically an input layer and an output layer with one neuron, actually, one output neuron. There was an input, values for all the nodes, that's a vector. If you take the nodes together, right, it's a vector. And then you have weights that connect the input nodes to the output node. Take all the weights together, that's a vector, a weight vector. So you have two vectors. Well, reserve some variables in the current system that we're using for them, okay? Vector contents, we have variables for that. And then he wants to come up with a prediction by this neural network after training. The prediction could be whether this is a spam email or not. And the sort of the parameters of the email are given by the input vector, okay? The prediction could then be a scalar, like 1 or -1 for spam and not spam, okay? So have a scalar value reserved for that. And then maybe you also have the true values. This is really a spam. This is not a spam, okay? This will be again a scalar. You can represent it again by 1 and -1. Why not, okay? So you have linguistically all that you need to express what he was doing there, okay? And then there's two things that the perceptron does. It gives you a prediction whether this is a spam email or not. And secondly, you can train it. That's also a kind of long-term belief revision. And both kinds of belief revisions you are able to express in the system now, okay? So I'm now giving you the axioms, the postulates that you would have to add to my logical axioms to get perceptrons out, okay? So that's not how Rosenblatt writes them up, but that's how I want to write them up, okay? So the idea is, if the similarity of the input vector at time k, because you can do that at lots of times, yeah, is similar enough, if the input vector is similar enough to the weight vector, if their similarity is great enough above the threshold, then predict that it's a spam, okay? So roughly your weights vector is where you are, your current doxastic state, right? And it sort of determines, that's what you believe spam email is like. You check for the similarity of the input to that weights. If it's large enough, predict the spam. If not, predict that it's not a spam, okay? So the negation, that's the minus vector, or the minus scalar in this case, -1. And that's it, that's the prediction at this point of time in k, okay? So you can write it up as a belief revision, a short-term factual belief revision, right? At the beginning, the system doesn't know anything in terms of whether this is spam or not. You get the input vector, you revise with it. You can express that revision by conjunction, and you add the prediction value here, okay? So it's a kind of non-monotonic inference. And you can write it up in the system by conjunction. And then next point of time would come along, and new prediction, new input, and so on. But what is more interesting is there's also learning going on in the perceptron, right? That was the interesting thing, a long-term belief revision. And again, you can write it up in the following way. So you say, if the true value, say you can then check, was it really a spam email or not, okay? If the true value is identical to what you predicted, leave the weights the same. So the weights at the next point will be the old weights, yeah? If you mispredicted, and the true value was a 1, so it was a spam, but you predicted, no, it wasn't a spam, okay, then what happened was, so you said it wasn't a spam, so the input vector was not close enough to your current weights, okay, but actually it was a spam, then you should change your weights, right? You need to learn, and you should make your weights more similar to what the input was like, okay? And you can do that by belief revision, by conjunction with the input plus some coefficients, okay? So the belief revision is by conjunction and the input vector, as it were. And if you mispredicted, but it wasn't a spam, it's the opposite. Your weight vector was sort of too similar to the input. Okay, that wasn't a good idea. Make it less similar to the input. And you can do that by revising with the negation of the input. That's the sort of the inverse vector. So again, you get belief revision by conjunction and negation. So you can see I can write up short-term prediction and learning in the perceptrons in perfectly logical terms in my system. Okay, so the system with these axioms will be able to derive everything that the perceptron does. Okay, but in logical terms, as it were. And that I find cute. And now you might think, okay, but that's perceptrons. Don't we all know that perceptrons are, you know, much too simple? We can't do real machine learning. That's true. But here, say a slight extension of the system by one non-linear function symbol, sigma, it's for the logistic function if you're interested, okay, will enable my system now to express logarithmic regression, which is probably the algorithm that your spam filter is really using to determine whether it's a spam or not, okay? So I don't give you the details if you're interested here. You can ask me later, but the idea is slight additions of the system will allow me actually to logically write up in very much the same way modern algorithms for machine learning, for prediction and learning in a logical system, okay? The only thing that I need is I need some nonlinear function symbols around as well, okay? So with that, I want to close. Let me sum up. I wanted to argue that the first order theories of vector spaces and real closed fields can be presented as reasonably well-behaved logics of vector space models. Okay, the resulting system can be used to logically reconstruct belief revision and similarity of contents and neutrality and strength and induction and conditionals, and I hope way more. There's a probabilistic interpretation, and it might have some nice applications in cognitive science, right? Remember the Linda example and the Queen example. And the whole system might take us at least one step closer to a logical reconstruction of certain aspects of machine learning. There's a nice talk by Johan van Bentham where he says this is one of the challenges that logicians face in the future. Can we reconstruct machine learning? I agree with that challenge, and that's my way of taking up the challenge in at least one possible way, okay? And I think there's a lot to do. That's just the beginning, right? So there is other interesting consequence relations that we can now define and study, okay? I haven't told you about disjunction. Well, add it to the system, okay? Instead of just having propositional variables, why not have predicates and singular terms as we're used to, okay? I want to have operators and quantifiers for linear transformations, okay? And then I want to have some nonlinear function symbols around, like for exponentiation, because that's what I would define, for example, to have my logarithmic regression ultimately being represented in the system, okay? Once I've done that, I should be able to logically reconstruct machine learning in proper artificial neural networks with backpropagation, the whole cool stuff, okay? So, you know, that's a nice prospect, I hope. And then, as for us philosophers, there should be a lot of philosophical consequences, right? So for semantics, what's meaning in this perspective? Well, it's a vector. It's not a set of possible worlds. It's a vector, okay? Or is this still logic? Okay, it's a kind of, you know, more relaxed understanding of logic that I've presented. Does it make sense? Okay, good question. Or epistemology, you get a new system of belief revision. Okay, it's neither the good old HEM belief revision, nor is it necessarily probabilistic. It's sort of somewhere in between, and that should be interesting. Okay, and so on and so forth. So with this thought, let me thank you very much, and let's see what you think about it.